Episode of Simuleo. Sorry about that. I accidentally closed stream instead of switching to a different scene. I don't know why I did that. For some reason, I'm just off today. We'll see how it goes. Right, so what are we doing today? So today we're actually moving on to the next algorithm, which is an algorithm we were doing before, the Gauss's Easter algorithm, actually. We did it, let's see, how do I put this? We did it for a few months, and then we had to stop it, and now we're going to come back to it so we can go ahead and finish it up. So the first thing I'm going to do is I'm going to cd into projects algorithm archive, git status, git checkout master, and git pull org master. So I'm just going to pull the latest from the master branch of the algorithm archive. And then what I'm going to do is I'm going to git checkout IFS for iterated function systems, which is what we'll be working on today, and git rebase master. It should be fine. I don't see any reason why this would, git status? What? Oh, we both modified literature.bib. Okay, that's fine. Literature.bib. Look for head. Let's see, we have it here. Right, so we definitely want all these guys here. And let's keep going. It should, yep, here. And we also want the ones for IFS. But I'm not exactly sure why it did that, but that's fine. G down here and DD there. Okay, cool. So this should be everything that we need for, this should be everything that we need. However, I need to check something really quick. Yeah, I did a different commenting scheme for one group and the other group. So let me just go ahead and fix that as well, because I don't even understand how I could have two different commenting schemes. But apparently you can. So let's just add this in here, that, this, and that. And now we're going to do, 78A dash. We're going to do the same thing down here. Cool. Okay, so now the literatures should be up to date. Let's go ahead and finish the rebase in. Git add literature.bib, git rebase continue, and git log. Okay, seems fine to me. So now what we're going to do is a git book serve over here. Oh, cd into projects, algorithm archive, and we're going to run a git book serve, and we'll go from there. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. As soon as I see it in chat, I'll do my best to answer it. Okay, let this run, and let's see what we got. Okay, wait, what? I swear there's more than... Okay, well, let's just see what this looks like. I've got a feeling this isn't the right... We'll see. I don't know what I just clicked on, but it was not what I meant to click on. Let's go back. Cool. Okay. So let's see. We should have iterated function systems in here. Cool. That's what I expected. And then we should also have computers down here. So now I am... Okay, let me check something really quick. Hey, Athal, how are you? So let's go ahead and git checkout master. It says 46,216 words there. Let me see how many words master has, because I thought master had that same number of words, 44,000. So this chapter is only... Oh, okay, fair enough then. Git checkout IFS. This chapter is only a few thousand words. Interviewing for a research role today? Oh, cool. Yeah, have fun. Yeah, I hope it goes okay. What exactly will you be researching? I assume, if I remember correctly, I feel like it's going to be more biology focused. But yeah, feel free to talk about it in chat. I'm more than interested in hearing about it. Okay, so it's a new microbiome group. Interesting. So is this more experimental work, or is it? Because I swore you were more. I mean, I don't know. I actually don't know how. I guess there isn't so much biological theory, bioinformatics. This will probably be more algorithmy. Cool. I hope you enjoy your time there. Right, so just to catch anyone up who may have missed the past few streams, I've recently been working on the Easter algorithm, also called Computus. Obviously, Easter happened this past weekend, so there isn't really a need to really talk about this algorithm anymore. It's super interesting. I would definitely recommend you checking it out if you can over on the algorithm archive, and I'll link it over here. Well, let me go to the algorithmarchive.org. And then we'll move down to Computus down here. Okay, here you go. So this is the latest chapter put into the algorithm archive. Now, the reason I bring this up is because I did genuinely do my absolute best to get a video out this weekend. I just couldn't do it. I should have known couldn't have been able to do it, right? Because if I look at all of the past videos I've ever made, I have not been able to both do all the video recording and voice recording and everything and the editing within the same day. And so after like a full day of just kind of trying my best at it, well, maybe not a full day, but most of the day I spent trying to figure it out. At about 3:00 p.m., I finally threw in the towel on Saturday, and I just said, yeah, there's no way to get a video out on Sunday. And on Sunday, of course, it was Easter. Look, I mean, I could have done what I could have to get the video out on Easter, but I spent the time with my family, and there were tornadoes that were going to be coming through Alabama, so we had to take shelter actually at my sister's house the night before, or the night of Easter. So that was why I didn't stream yesterday, because honestly, I was just incredibly tired. We didn't get much sleep at night. Basically, everyone went to bed at roughly midnight, and we had to leave at 6:00 in the morning. So between those two things, like at most, I got 5 hours of sleep, and I think that's generous. So I was just exhausted yesterday, and I needed to figure out what I want to do for scheduling and stuff anyway. So that's why I didn't stream yesterday. But today, we are going to be continuing the iterative function system stuff. There's a lot of really cool stuff going on here. So I'm deciding how I want to run today's stream, because we do have a lot of things to do. This is the wrong version. This is what I'm looking for. We do have a lot of things to do. But luckily the chapter is mostly written already. I'm pretty, if I remember correctly, I'm pretty happy with how this chapter read off last time. There's some small things that we have to do. In fact, a lot of things we have to do, a lot of images we need to generate. And I think that's going to be the bulk of today's stream. So that's what we'll be focusing on. One thing I know I need to do is add a little snippet of code down to the bottom of this file so that the math renders without you having to F5. So let me go ahead and do that right now so I don't forget, because I always forget. So we're going to cd into contents, ifs here, ls, and we're just going to do a quick, I think I can just tail. I think I can just tail computus. Let's just see what happens if we do that. Computus, and then we're going to tail computus.md. It is, let me just open it up. vi computus, and then computus.md, a G down here, and where is it? It should be, there it is, the script guy right here. That's what I need. Quit there, and let's go into vi ifs.md, and we're just going to paste that down here at the bottom. Okay, there is a lot of stuff that needs to be done. For this particular algorithm, we need a lot of visualizations to be made. We need to write the source code, which is mostly written, but we've got to revise it so it's a bit cleaner and easier to understand. And then we also have to do a lot of revision and stuff like that. But I think, unless I'm completely wrong here, I think we can get all of the resources necessary this week. And so I'm hoping this weekend I will be able to do the voice recording and get the video and stuff, so that next weekend, let's see, what day is it today? Today is the 15th of April. 15th of April, Japanese Standard Time. So it's the 14th of April, my time. So that means that probably on the 26th is when I'm going to shoot to get out the video. I'm going to try to get the video out Sunday morning. Although admittedly, probably Saturday morning would be better for everyone, but I'm going to try for Sunday morning. So Sunday the 26th, I think that's the date I'm going to shoot for this video. But unlike the Easter algorithm, this doesn't actually require a huge, like the deadline isn't as strict, right? Like, as long as the video comes out, it comes out. And at this point, I'm going to be honest, as of last year, the reason I stopped making videos was, there was a number of reasons, but this was the last video I tried to make before I stopped making videos entirely. And I know what you're saying. It's been a super long time since my last video. And so I figured let's just go ahead and get this done. Athal, the supervisor uses Rust as his algorithm language of choice. Oh, cool. Yeah, seems fine. Honestly, don't take this the wrong way, I've never actually seen someone using Rust for scientific computing before. I kind of wish people did more, but I just haven't seen it be used. So I'm not saying it's a bad language. It's a great language. It's just I don't ever see it, I guess maybe because most of the stuff I see is for GPU computing nowadays, but, it is what it is. Okay, we're going to write and quit that. I'm not going to look too much at the algorithm archive right now. I'm just going to kind of probe around to see what actually needs to be done so we can create a list of things that we need to do. Actually, let me take a look at that article. I need to see what images need to be generated as well. I accidentally closed the tab. I was going to keep the tab open and then just look at it and then go from there, but I accidentally closed the tab because I'm an idiot. So let me get some water. I'm not sure how long today's stream is going to be. We've got a bunch of things to do. The first of which is just to figure out the schedule for the next few days to make sure we can get everything done on time. And then after that, we will, I guess, just start working on the iterative function system stuff. So let's do localhost. Yep, here we are, 4,000. It's felt like no time at all to me, Simulical. Wait. Oh, you mean since the last time I put up a video? Yeah, that's because you weren't waiting on my next video. Like so many people on my YouTube comments. You know what I might actually do? I might actually read through this, just to get an idea of what I was going for, because it's been about a month since I looked at this article, and so that might be what I do. I might just read through this and see what I have, and where I wanted to go with it, and see if there's a list of things on top of the images I already have here that I also might want to talk about. Right? This year's gone by so fast. Yeah. Right. So what I meant to say is I tried working on the iterative function system stuff February of 2019, not February of 2020. So I've been working on this technically for a full year. That's how far behind I am. But yeah, it's okay. We'll see how this goes. Cool. Okay, so I'm going to read through this, and I think that's what we'll do for the first bit of stream, just to see what what I was thinking about doing before, and what the set of images are that we need. And I guess I'll write down the set of images on this sheet of paper. On the other end, on the other side, I have a list of ab exercises that I do every day. So I guess this is a perfect place for it. It's not like I'm going to lose it. This year's going by so fast. Yeah, I mean, that's what happens when you get older. I don't know. 2020 is a weird year. It's a weird year, but so is, I don't know. It's weird for me. I think this year has been a bit different for me than it has been for many people, because I started my job in January, right? And I was really gunning. I was doing everything I could to get my thesis out on time so I could start this job in January, and I started the job in January, and then, the coronavirus stuff picks up late February and maybe March, and it's just been a rough year. Rough. Fetch me a coffee. How is a year weird? I don't know. It's weird for a number of reasons. It's a leap year, which means it's already, 25% better than other years. Or how does that work? It's a leap year, which is, only one out of every 4 years roughly is a leap year. So that's already special. There's been a lot of weird things that have happened. People have gotten out, just been pushed out of their jobs and work and all that kind of stuff. But I don't know. Okay, so let's go ahead and read through this chapter, see where it's at, and what we need to do with it. Also, for the record, I am going to be putting this video up on YouTube. I have been putting a lot of the videos recently up on YouTube on my second channel, just youtube.com, I think /user/Simuleos will get you there. YouTube, so here's Leos OS. I'll go ahead and give you guys a link to Simuleos here. There you go. So here's a link to Simuleos. Again, the last video I just put out like a second ago. Well, okay. I put out like 14 videos specifically to calculate the date of Easter. It's just ridiculous. I'm going to buy a new phone with my stimulus check. That's pretty weird. Right. I think I get a stimulus. How did you get it? What is a stimulus check, actually? I haven't been keeping up with this. Well, how to get a stimulus check. I think I'm... Let's see, how to get a stimulus check from the U.S. government, which could pay up to $1,200 if you qualify. Let's see. Have a social security number. File a tax return for 2018 or 2019. Yeah, I can't do that because my tax return... I only made Japanese yen, so I don't have anything to... Yeah, I don't have anything to do there. So I can't file a tax return. So that means I'm not getting a stimulus check, which is fine. It's fine. Right. Oh well, it is what it is. Dang. You can file a return without paying taxes. If you're citizens, you still paid U.S. taxes. Right, but No? Wait, I need to think about that. I did file taxes every year, but every year when I filed taxes, it basically just asked how much money do you have in Japanese yen, and I gave them an amount, and then they didn't have me pay anything, because it was under the threshold that they require to pay. So the answer is, I like. It's just a weird situation. I don't know. I guess I haven't. I mean, I do file taxes. It's just that every time I file the taxes, I don't get anything back from it or anything, and I don't have to pay anything. So it's just how it goes. I don't know. I'll figure it out later. It's not essential. Okay. Just file $0. Right. The problem is if you file $0, then you owe the government $3,000 or something dumb like this. It's actually a pain in the butt. Like, it's because of the Obamacare stuff or whatever. Like at some point I just filed that I had no U.S. income. And then I owed like $1,000 because I also said I don't have health insurance, which I didn't, have U.S. health insurance. So then, yeah, it's fine as long as they have a record of you. I don't know. We'll see. I'll look into it later. It's not, it doesn't matter at all. Okay. So, what am I going to do? I'm going to read through this chapter on the algorithm archive and see what we need to do. Okay, so for the record, this is kind of pulling off of some of the information that we talked about in the plotting chapter. Hey, Gibbous, how are you? So there's a lot of information here, like a lot of information. This is one of the longer chapters in the archive, actually. Iterated function systems is way shorter than the video on, or the discussion on computers. I don't know why, but computers ended up being quite long. I imagine it was long predominantly because it's just a lot of history information that we have to talk about. But overall, we'll just see how it goes. I was thinking about the concept of a genre. Oh, cool. Yeah. Okay, so let's go ahead and read through this, and we'll get through it. And then we'll start working on the visualizations, which I know most people are here for, right? Hey, Happy Little Rat, how are you? I feel like it's been ages since I've seen you on stream. I hope you're having a wonderful time. And yeah, I hope everything's going okay for you. Okay, so iterative function systems. A few quick notes before we start. 1, for this chapter, we'll be following the methodology set out by the plotting chapter. Let me click this link to make sure it works. Yep, seems to. That is to say that the code presented in this chapter will output another file that can be easily plotted by an external plotter. If you like to use a plotter provided by your language of choice, please modify the code provided to do so. This chapter is currently a subsection to the plotting chapter, but we may extend the algorithm archive in the future to other fractal generation methods, which would require a new section on fractals in particular. This would include a chapter with more rigorous definitions on fractals, which is largely missing from the following discussion. Please let us know if you're interested. In this chapter, we will show you how to make some of the most famous fractals via iterated function systems, the Sierpinski triangle and the Barnsley fern. We'll also introduce a number of interesting concepts for further exploration, such as chaos games, Hutchinson operators, and attractors. Right, so let's see, what do we have here? I actually have no idea what your stream is about. It's my first time here. Oh, hey. So my stream is primarily about, well, the algorithm archive. It's here. Between YouTube, so, youtube.com, LeosOS, between my YouTube channel and the algorithm archive, basically we just talk a lot about algorithms and methods, and that's kind of the whole thing. We just learn algorithms together as a group. That's the whole thing. Right now I'm working on iterated function systems, which are ways to generate fractals and fractal-like structures, but really it's just to generate anything, weird patterns and stuff like that. That's kind of what I do. Okay. All good, just awfully busy. Yeah, I totally understand that. Form genres describe the structure of its subject, like first-person shooter and electronic music. I'm not Dodo. Hello, I'm not Swak, if anyone remembers. I do remember you. How have you been? Fetch me a coffee. Thank you so much for following. Really appreciate it. Genres are just clusters in feature space. That is a wonderful way to put it, actually. Like, if you could do... Oh, I totally want to do this. You could do like some sort of affinity propagation or k-means clustering of genres, and yeah, that'd be interesting. That's a cool way to put it. Function genres describe the effect of its subject, like horror game and dance music. The most rigorous genres are a combination of form genre and function genre. That's so cool. Both genre subtypes can be a single feature or a group of features. Right. That's it's interesting, right? Okay, so now we're going to actually start reading through this chapter. So I had it set up. So we first start by talking about the most famous fractal, which, in my opinion, and I maybe you could debate this, but in my opinion, the most famous fractal is the Sierpinski triangle, right? So we talk about how you could generate the Sierpinski triangle, and then we extend the Sierpinski triangle to a square. And we show that if you extend it to a square, well, okay, it doesn't exactly work with the square, right? And we'll describe why in just a second as I go through this, right? Then after that, we talk about chaos games and attractors, and we explain what an attractor is through the lens of a chaos game, right? So here we simply talked about the Sierpinski triangle, and I think in essence, for iterative function systems, we don't really need to talk about anything but the triangle. So let's go here and let's actually remove notes of the Barnsley-Fern, because I don't think we need the Barnsley-Fern for this discussion. Let me go ahead and write that. Got a Mandelbrot set. Okay. Fractal. You're right. Maybe you're right. Let's see. But okay, maybe you're right. Famous fractal. Yeah, you might be right. Maybe Sierpinski isn't the most famous one. Yeah, we should debate that. That's worth debating. I mean, it is here on the list of famous fractals, but you're right. Maybe Mandelbrot is more famous. So let's say the most famous triangle, which also might not be true. Maybe we don't say anything about we just say the Sierpinski. Is that right? Or is it Sierpinski? Sierpinski or Sierpinski? I always get them mixed up. Triangle. Sierpin. It is Sierpinski. At the very least, I need to be consistent with my misspellings. Most famous IFS fractal. We could say that, but also just the Sierpinski triangle is fine. I'll get the N later. Maybe. We'll see. Okay. I'm okay just studying long hours. I barely have time to use Twitch. What about you? You're in Japan, I guess. Are you back in the States? Yeah, so right now I'm working for MIT. Yeah, so I just went from OIST, the Okinawa Institute of Science and Technology, to MIT, which is out of Boston. However, for the quarantine, I'm actually in Alabama, which is where my my family lives. I just drove south for the quarantine because I just didn't like my place in Boston, so I had to do something about it. Right. Let's see. Followed by the Mandelbrot set, and Mandelbrot set. Right. Cosmic Star Dream, thank you so much for following. Really appreciate it. Do you own a banjo? I do not. I definitely do not. I don't understand why you would... This is not unrelated, I guess, to the spelling of Sierpinski. This is just from Alabama. He's not a real Alabaman if he doesn't. Nice. Cool hair, by the way, gotta say. Thanks, I'm not a dodo. Appreciate it. Actually, I don't want to seem vain, but, yeah, so here's the thing. I've been wanting to grow out my hair since I was like 10, and this is like the perfect time to grow out my hair because like I can't cut my hair anyway, so might as well do it. And then like everyone's just been making fun of me for it, and I'm like, oh come on, like I don't think it looks bad. I think it looks pretty good. And then everyone's just like really making fun of me for it. And I'm like, come on. And then I Skype my girlfriend, and my girlfriend's like, actually, you know, your hair looks kind of good. And I'm like, thanks, but like it's only me and my girlfriend. It's only me and my girlfriend that like my hair. Everyone else has just been like really mad about it. I'm like, come on. Anyway, he's friends with Destin Stanley from Smart Every Day, so that gives him Alabama nerd cred. Destin's amazing. This is the perfect time for you to grow an apocalypse beard. I'm thinking I might grow the beard as well. My hair has been the longest in the family since I was 7. Wait, are you? Yeah, I mean that's fair. I just want to try long hair just once in my life to get it out of my system. I want to try it. Let's see. It's great. The problem is that there's a divide between short and long where it doesn't look as good. Right. That's true. Right. Right now it's in that awkward growing phase, so I understand that. But I'm trying it, so we'll see. It's gonna be bad, but we'll see. Academic nerd cred, it'll add up to great success. I don't know if my nerd cred is... I have some academic nerd cred, but it's mainly the... how do I put this? It's mainly... like science communication nerd cred that I have. I got my hair shaved yesterday. My dad shaved it, and it looks terrible. I've never had my hair this small. I haven't trimmed my mustache for like a month though. Yeah, so I know. So I have a number of haircuts that I know look bad on me. Like, for example, a buzz cut, I know looks bad on me. My hair goes back here, forward here, up here. It just doesn't work. Buzz cuts do not work on me, you know? And so I know that, like, kind of medium length hair doesn't work either. So I'm like, let's try long hair. It's going to look bad. But I think by the end of this whole discussion, I will have realized it's not my hair that makes me look ugly. It's just me. I'm an ugly person, you know? Like, I need to figure that out for myself, though, you know? My hair's super long when it's in the process of growing out, that is. Yeah, I agree. I prefer medium hair over short hair, too. Long hair will awaken your latent psychic powers. Hey, Trash Talk, how are you? My wife cut 10 centimeters off my hair. Now it's only still long. Anyway, this isn't a discussion about hair. Someone in chat, who was it, commented on my hair, and I just had to say that, like, I'm not usually this vain. Like, I don't like being this vain, but sometimes I get kind of sticky about it, you know? Anyway, so we're going to keep talking about the iterated function system, and we're going to see where we go. So let's write this, and we're going to figure out what images need to be generated, and I hope you guys tell me whether you think that this discussion makes sense, right? And we'll see how we go. Hey, Matt Triangle, how are you? I hope you're having a wonderful day. Did you finish your PhD? Right, yeah, I did. So I finished my PhD in December 2019, and again, I've been working at MIT since January 6th, 2020. It took about a month of onboarding before I really started doing anything crazy. And, you know, then we traveled for 2 weeks, and then there was COVID. So honestly, it's just been a lot of stuff keeping me from doing, like, actual work. But I've been thinking about doing some live streams for my project, my research project. So that might be coming in the near future. Let's see. Honestly, hair is the least important thing on a human being. It's the inside that counts. I agree with that statement. Like, I mean, the truth is, I've never actually looked at someone and said that person is attractive. You know, like, it's just not something that comes to my mind. You know, I can look at someone and say, I don't know, like, I don't look at people and think, that person has a bad haircut, or this person's attractive, or this person. It just that's not what comes to my mind, you know? But what does come to my mind a lot of times is the way that they move, the way that they act. Like, yeah, I can see, like, some people just move a particular way, and it's fun to hang out with these people because they have, I don't know, like, the way in which they walk or they present themselves. These are things I do see, you know? And I find certain motions attractive. You know what I mean? Like, I don't know. I don't mean to harp on my girlfriend. I really like my girlfriend. She's a wonderful person. And, like, that's the first thing I noticed about her. Just the way that she moves around is it's just cute. That's all I can say. Like, there's something about the way that she moves that I really appreciate, you know? I don't know how else to say it. Like, it's just, like, weird things. Like, you know, when you give someone a fist bump, how you go afterwards or something. It's just, I don't know. It's just, I don't know what I'm saying. All I'm saying is that I don't take physical appearance too much into account. But there is something about the way people present themselves that I do take into account, and I don't know what that is. I don't know how to distill that into an essence and say, this is what I find attractive about this person. But it's certainly not, like, if you just give me a picture of someone, I'm not going to be able to tell you if they're attractive or not. But if you show them moving, then I can, you know? I don't know why I'm rambling about this. Simulus, I just realized you could fudge it with one of the most famous fractals. I could, but at this point, we've already changed it to the Sierpinski triangle, and it's, you know, this isn't open source. There's no way we can change it. It's too hard. It's too difficult. I remove the hair on humans before I eat them too. Oh man, that's not what I was talking about at all. My digestive tract is looking good right now. Oh boy. It's been a while since I've been in stream. I changed jobs. Oh cool. What are you working on now? Cosmic Star Dream. COVID all caused by people eating bats. Vegans would have saved us this torment. Oh no. Let's not have that discussion. The truth is I've never actually looked at someone. I've looked at some people, and just not often. Current situation has bonus points. Nobody has tried to ask me to come meet them. Oh yeah, fair enough. Actually, I kind of like working remotely. If it wasn't for the fact that my neighbors are super loud in Boston, I actually would have genuinely liked the experience, you know? Just flip your hair every 20 seconds, drink weird drinks, and wear leather. You can totally rock this hair, man. Thanks, Cobalt. That thing looked good. Thing that looks good now will appear ridiculous a few years later. Kind of like mullets. Oh wait, I know. No matter what you do, it's gonna look ridiculous. So you just gotta do it. You know, you just own whatever you look like, and just, that's my opinion. His vision is based on movement. He's a T-Rex. I used to work as a GPU research engineer. Now I work as a software developer at Unity. Oh, Unity, that's super cool, man. Also, GPU research engineer was also super cool. But I'm cool. Good job. Keep up. I mean, keep up the great work. Simuleos Rex. I like the way. I like it way more than low-level programming, honestly. Right. I mean, that's also one of my issues with GPU programming. Like, if you just want to code up an algorithm, the GPU gets in the way of programming this thing always. Now, sometimes that can be very like there's a level of joy in figuring out how and why the GPU works the way it does, and how to get your method to work in a massively parallel fashion. There's a lot of this that's actually very fun, but it's like the same puzzle over and over and over again, and it ends up being that sometimes you already know the solution. It's just going to be a lot of grunt work to get there, and I can understand. I totally understand. That's why I'm using Julia now, and I'm kind of no longer using CUDA, you know? Okay, so let's start. The Sierpinski triangle. To begin the discussion of iterated function systems, we will first discuss what might be the most famous fractal currently known, the Sierpinski triangle. This is where I'm going to change this to one of the most famous fractals. One of the most famous fractals currently known, the Sierpinski triangle, shown below. Add image of Sierpinski triangle. If you guys haven't seen the Sierpinski triangle before, here you go. Sierpinski triangle. Here's the triangle. Bam, that's the image I'm going to put in there. Okay. This image is clearly a set of triangles embedded in a larger triangle in such a way that it can be continually cut into 3 identical pieces and still retain its internal structure. This idea is known as self-similarity, and it is usually the first aspect of fractals that will catch an audience's attention. In fact, there are plenty of uses of fractals and their mathematical underpinnings, such as estimating the coastline of Britain, identifying fingerprints, and image compression. In many more rigorous definitions, a fractal can be described as any system that has non-integer Hausdorff dimension. Though this is an incredibly interesting concept, this discussion will focus... the discussion of this chapter... So the discussion of this chapter will focus primarily on methods to generate fractal patterns, and will refrain from delving into this discussion for now, and instead focus on methods by which fractals can be generated through iterated function systems. Okay, let me fix this sentence. It's just wrong. I'll fix that. Estimating the cosine of Britain. Yeah, the British cosine is different than the American cosine. It's one of those weird subtleties between Europe and the US. Oh, I guess Britain is not in Europe anymore, right? Is Britain in Europe? Did Brexit actually happen? I'm sorry, I'm an ignorant American. Please correct me. Let's see. There's a lot of friction in GPU programming. That's true as well. Have you worked with Scala? Scala. No, I've not worked with Scala. Maybe I should. This reminds me, I should try learning how to program with brain. Dude, it's a wonderful language. I wish I knew more about it. Higher level makes me more happy, to be honest. That's fair. Sierpinski, not Sierpinski. Sierpinski? Oh no, I probably screwed this up everywhere. Sierpinski? Okay, wait. Maybe it's only this one. Sierpinski. It was only that one. Wow. Okay, for once I actually spelled it right. Am I correct in my observation that when you code something for a CPU, you can pretty much be as high or low level as you want? But with GPUs, there's just some form of low levelness you can't escape. Why is that? Is the software for GPUs lacking behind? Okay, there's some truth to that statement, right? So let me see what Happy Little Rat says. GPU compute is just a temporary step towards something actually useful. Well, okay, I don't know if that's true or not. That depends on your opinion. GPU compute for graphics, I agree. GPU compute for high performance computing, I actually feel like GPU computing is like one of the perfect forms of massively parallel computing. I think I think we're actually getting close to like the perfect architecture for massively parallel computing and stuff. I'm going to get to your question, Cobalt, in just a second. Let me catch up on chat, and then I'll come back to it. I misheard. Can you please give the link to the website that you're using? The algorithm archive? Yeah, it is right here. It's right here. So this chapter is not yet available on the algorithm archive, so you're gonna have to build it yourself. But this is the main website that we're working with. Unless you were talking about a different website, maybe you were talking about Twitch. I'm also using that website, but I think you know about that one. Let's see. I feel like it's a bit weird to throw out non-integer Hausdorff dimension like that and just skate by it. Yeah, maybe Okay, we'll talk about that in just a second as well. So let me write that down. Let me catch up on chat. And then I'll answer Cobalt's question, and then we'll talk about this. Brits are still in Europe, just not the EU. Oh, right. I don't think the people from the UK know either. Did it finally happen, or was it just a fake out? They're still in the EU. It's definitive that they exist somewhere this year. Technically, they are now in a transition period. Okay. Cosine, let me see, of Britain. Equal sine of Britain over tangent of Britain. But they left FOF, intensive purposes. Oh, for all intensive purposes. If GPU computing is to be useful at all, it is necessary to be threaded, and threaded code is always going to be low level under current programming paradigms. Right. I think Gibbous actually gave the best response to Cobalt's question about GPU programming being more low level. I think that's just how it is. With GPU programming, you basically tell each core on the device what it's supposed to be doing, right? And this is hard to do when you've got thousands of cores, right? So the difficulty here is basically taking your algorithm and splitting it up into a bunch of little chunks and then interfacing with a language that allows for you to talk to your GPU in a fast way, right? So like, for example, if you have a for loop, I'll just throw up Zernal PP and we'll talk about it. Just for a second, I mean, I love answering questions like this. So like if you have a for loop, for I equals 1 to 1,000, something like this. So no matter what your notation is, this is the notation I'm using, right? In a lot of languages, you can do like a pragma, something like that, you know, blah, 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 blah. You can basically set this for loop to automatically do, for example, I equals 1 will be on processor 1, or I equal 2 will be on processor 2. Languages exist, like OpenACC, Open, let's try that again, ACC, or I guess programming paradigms exist, like OpenACC, which will easily distribute your loops and stuff like that across GPU programming. That's the thing. OpenACC is like OpenMP. It's similar, but OpenACC is kind of for GPU, and OpenMP is more for distributed CPU. Right. Intel TBB. I don't know about that one so much, but maybe I should. So you can kind of write the code that you would write for a CPU. The problem is on the GPU, you have to think about it a bit more. Like iterative stuff on a GPU doesn't make sense. So anything that's iterative doesn't make sense, and recursion also doesn't make sense. I think until like CUDA 4 or 5, you weren't even allowed to do recursive things on a GPU. So if you have an iterative or recursive method, you have to rethink how this method is done, because each individual core is very, very weak. So if you have an iterative thing where process 1 has to happen, then 2, then 3, then 4, then 5, it's hard to distribute that, right? So this has to be done on a single thread, and each thread is weak, so not much happens, right? So I guess my point is, when it comes to GPU programming, you really do have to wrestle with the hardware. No matter what you do, you have to wrestle with the hardware. By the way, Jack Weaver, thank you so much for following. Really appreciate it. So yeah, that's it, Cobalt. It has to do with two things. One, it has to do with what Gibbous said, in that interfacing with the hardware is hard because you have to do it at a thread level. And the other thing is what you hinted at, in that the programming paradigms are just not as well sussed out here. You know, that's the other issue. And again, OpenACC exists, but most people will use CUDA or something like that, or OpenCL or something like that. Again, I'm speaking specifically from high performance computing and compute discussions. Although OpenGL also has shader, the Open Shader language or whatever it is, GLSL, which allows you to do this type of computation as well. Happy Little Rat can talk to you way more about how to do that kind of stuff than I can. I don't know how to use the graphics languages at all. I just use CUDA and do GPU computing in that way. King Div, thank you so much for following. Really appreciate it. Let's see. GPU computing is to be useful. It will be necessary. British angles are meter, and American angles are foot. So if it's just, so it's just a work division problem at this point that's keeping us back? In a way, you could say that. Also, GPU computing is only useful for massively parallel stuff and doesn't lend itself well to many algorithms. That's true as well. Simple things like doing a transpose and stuff is insanely costly on a GPU, and there's a lot of things that are just insanely costly on a GPU that you wouldn't naturally think of as being costly, right? On the CPU, you tend to minimize your compute footprint by focusing a lot on manipulating memory and stuff like that. Whereas in the GPU, it's the other way around. If you can recompute something to save a little bit of memory, you do that, which is weird when you think of the CPU perspective. A couple of technical paradigm problems. Got it. Yeah, I'm hoping it helps somehow. But transpose is easy. Oh, no one. Okay, look. Even for distributed CPUs, transposes are still the sticky part, right? Like it's hard. Like every single time. So one of my friends is working on this thing called kernel abstractions, which is a new way to write GPU or rather heterogeneous computing, both GPU and CPU computing in Julia, right? And we were talking about what we need for different things, and I had to write examples. And at some point, he said, "I think I'm going to do X," and I was like, "Well, what about the transpose?" And he's like, "Crap." Every time you think about the transpose, it just bucks everything. It bucks the trend. It's hard. Ethereal Dratini, thank you so much for following. Really appreciate it. A GPU, like a CPU and the human brain, is a computer specialized for a specific type of problem. Looking forward to QPU. Actually, I don't know when QPUs are going to be a thing. So quantum processing units. The split you have where some things are easy for a computer and hard for a human, or easy for a human and hard for a computer, that exists between CPU and GPU, I think. Something like this. Yeah, it's not as great of a divide, but definitely you could argue there is a divide between problems that are easy for one architecture but hard for another. I'm going to do something really quick. Sorry about that. I just need to check my volume levels, and it's kind of... Okay. I think my volume levels are okay. I just wanted to make sure that I wasn't peaking too much because I found that in some of my previous streams I was. Okay, so I think this should be fine. Okay, we're going to go back to talking about the Sierpinski triangle and iterative function systems. How can we expect to have a nice GPU stuff? We can't even do floats, right? Oh, floats. Like float 64 and yeah, no, I get you. I hear that all the time. A lot of people get really pissed off with GPU computing because sometimes they're forced into float 32 when they need 64-bit precision. I don't know. I understand the issue. Okay, so Gibbous mentioned something that it is weird. Let me reread this paragraph. So what we say, so we talked about the triangle being a subset of triangles. And then we say, this idea is known as self-similarity, and it's usually the first aspect of fractals that will catch an audience's attention. In fact, there are plenty of uses of fractals and their mathematical underpinnings, such as estimating the coastline of Britain, identifying fingerprints, and image compression. In many more rigorous definitions, a fractal can be described as a system that has non-integer Hausdorff dimension. Though I understand... You're right that it's weird that I just state this, but also I linked to 3 references in here, 6, 7, and 8, all of which discuss this. So there's three blue and brown, discussion about the Hausdorff dimension here, and then also a citation from Assessing the Roughness of Time Series and Spatial Data from JSTOR. JSTOR? I actually don't know that too much. Sayugi, thank you so much for following, really appreciate it. There we go again, cosine. I should say coastline. I just need to be better at pronouncing things is all. Maybe one day I'll learn English. I think maybe this is okay because I do cite where this is coming from. So if people have a question about this, the Hausdorff dimension, maybe I need to add a sentence about this. Let me just Hausdorff dimension. Let's add a sentence about it. I think it's just a fancy word for Queen of Britain. Okay. In mathematics, the Hausdorff dimension, aka fractal dimension, is a measure of roughness and or chaos that was first introduced in 1918 by mathematician Felix Hausdorff. For instance, the Hausdorff dimension of a single point is 0, a line segment is 1, a square is 2, and a cube is 3. That is, for sets of points that define a smooth shape or a shape that has a small number of corners, the shapes of traditional geometry and science, the Hausdorff dimension is an integer agreeing with the usual sense of dimension. What I can say here is that the Hausdorff dimension, by this definition, a fractal is any shape that... By this definition, a fractal is any shape that isn't a shape. A fractal is any shape. So the Hausdorff dimension is a way of displaying what a shape is by basically saying how many points that shape has. essentially, right? So like a square is 2, a cube is 3. So this would mean that oh man, this is it makes sense in my head. Because it's like a fractal is something that, so like a line is dimension 1. A square is dimension 2, right? So if you have a square, but you can kind of divide this up into other squares as well, then, okay, I need to think about how I'm going to write this. So I'm going to think of Hausdorff dimension as Hausdorff dimension to maximize memory retention. Fair enough. I understand that Hausdorff dimension is. I just feel it's a complicated piece of jargon entirely irrelevant to the topic at hand, which would make it rather distracting. Right, I see that point. But my point is that the actual definition of a fractal comes from what a Hausdorff dimension is, right? So the original definition comes from this point. Like the two definitions you have for fractals are 1, dealing with self-similarity, 2, dealing with non-integer Hausdorff dimensions, right? So when you think about it, right, I just described self-similarity, and then I just need to say at the very least that, you know, this other thing exists that also defines a fractal, and here are ways for you to understand it. Let me just put a to-do statement in here. To-do, describe Hausdorff briefly. Because I feel it's necessary to say that this is a way to define a fractal. Because without that definition there, we don't have the true nature of a fractal, right? I hate math. I'm so sorry, Cobalt. I hope maybe one day you'll learn to love it. This really makes me want to get back into doing fractal stuff again. Haven't been doing it as much since I'm working on my thesis. Dude, the thesis comes first. Work on your thesis, then do fractal stuff. But how's the thesis going? I hope it's going okay. Okay. So I just need to add a statement about kind of what that is, and then we can go from there. Love candy, though. I'm glad to hear that, Cobalt. Okay, so to start, imagine creating a triangle from 3 points, A, B, and C. These points can be arbitrarily chosen, but for this conversation, we will constrict them to vertices of an equilateral triangle shown below. So basically, I'm just going to point, I'm going to draw in Zernal PP what I'm actually going to draw here. So what I need to show is A, B, and C. So we'll say A, B, and C. That's all that image is going to be. Okay? Now, what we'll say is, now let's create 3 separate functions that can act on a 2-dimensional space. F1, F2, and F3. And all of these guys are P plus A over 2, P plus B over 2, and P plus C over 2, where P is within R squared, right? So this is a 2-dimensional value. So we say each function will be input in a particular location in space. Here, P is within R squared. And the output output a new location that is the midpoint between the initial location of A, B, and C for functions 1, 2, and 3, respectively. Wait, let me reread that. Each function will input a particular location in space. Here, P is within R squared. And output a new location that is the midpoint between the input location and A, B, and C. Okay, that makes sense. For functions 1, 2, I used and or separately there. That's going to bug me. Let me go ahead and catch up on chat in just a second, guys. Oh no, and is actually correct there. Okay. The union of all these functions, the set of all possible functions available for use, is often notated as the Hutchinson operator. And for this case, it would look like this. We just have the union of F1 through 3. By iteratively using this operator, we can traverse through all possible movements in the set. For example, let's use all 3 functions on all 3 existing points, which will create 9 additional points, many of which overlap. This operation has essentially shrunk the larger triangle we had before into 3 smaller ones, all of which have been constricted towards one of the vertices. An image of this can be seen below. A space N. Okay. So what I'm showing here in the next visualization is essentially that if you use function 1, so we'll hear function 1, which is going to be equal to P plus A over 2, you're going to create 3 additional points. So B is going to move over here, C is going to move over here, and A is going to stay in place. So you'll create a small triangle here, right? So you'll have a triangle here. And then if you use function 2, which we'll do in pink, which is going to be p plus b, let's over 2, you'll then have, a triangle here. And then if you use, let's do green, function 3, that's a 3. That's how you draw a 3. Is going to be equal to p plus c over 2. You'll have a new triangle here. Let's pretend that point's in the middle there. So this is the image I'm going to draw. I'm just going to show an animation of of all function 1s being acted, all functions 2 being acted, and all function 3s being acted. Let me go ahead and catch up on chat. My defense is on the 24th. Bring a sword. Oh, mine's on the 23rd. Dude, cool. Good luck, man. Both of you guys, good luck. What weapon will we bring? What's inside the box? You can tell me. A cat. Miniature houses containing dwarves, Kappa. I won't tell you, but if you see it, you die. Oh, no. All right, let me go ahead and catch up, or let me keep going here. So that's the next visualization I'm going to draw. So let me just keep this notated. So the first thing, again, I'm going to have to draw image A, B, and C. The next one, I'm going to have to draw, animate that movement. Cool. So let's keep going. Okay, so from here, each new point will spawn 3 children, and each child will move according to one of the 3 possible functions in the Hutchinson operator. Like before, this will cause each existing triangle to shrink and move to a new location. Here, if all the vertices on the left triangle are subjected to all 3 functions, 9 new points will be spawned, and 3 new triangles will be generated on the left edge of the previously existing triangles, as indicated below. So the next animation I need to do is here, if all vertices on the left triangle are subjected to all 3 functions, 9 new points will spawn, and 3 new triangles will be generated on the left edge of the previously existing triangles. So I need to show here, and this one's a bit more nuanced, but what I need to show here is that, if we use this triangle, let's go, I'm going to draw it here, and we do function 1 to this triangle, it'll generate a new triangle here. And then if we do function 2, it'll generate a new triangle here. And if we do function 3, it'll generate a new triangle here. So basically the point is that if we have a triangle here, it will always be in that position of the new placement, right? So it's always going to be in the lower left. It's just going to be moved slightly. So that's the next animation I have to do. Let me go ahead and catch up on chat here. What weapon will we bring? The city of Sodom being destroyed by... Oh, boy. Last message didn't get sent. It's Pandora's box, so all evil in the world is stored in there. I don't have any scientific basis, but I feel everything in nature is based on fractal-like structures or pseudo-random algorithms that may be based on something like DNA. I don't have any way to prove or disprove that statement. Because I simply don't know enough about this, Remember when trying to subdivide a triangle back in the good OGL days? Oh, the good old days. Wasn't the myth really about an urn, though? Oh, the Pandora's urn? Yeah, but, everyone just calls it a box. So, we'll call it a box as well. Okay, so let's keep going. After all the children vertices are subjected to all functions, 27 new points and 9 new triangles will form, creating triangles within larger triangles. From here, the children will then spawn 3 more children, and each of which will move according to different functions. These children will then spawn more children who act accordingly. All these processes continue on, and we begin to see an interesting pattern form. So the pattern, kind of the visualization I want to make here is that's not what I'm looking for. Sierpinski triangle? It's probably on this one. Kind of the visualization I'm looking to make here is... Hello? Okay, let's just do iterated function systems. Iterated. So let me find it, and let me repeat the same statements I said. So kind of the visualization I'm looking to make here is not shown in any of these. Maybe it's under Hutchinson operator? I know I've looked at this before. Hutchinson operator. Where would it be? I promise we had an image, or kind of. It's not under Hausdorff dimension. Would it be under? It has to be under iterated function system, and I must have just missed it. Iterative function system. Maybe it's under chaos game. There was a Wikipedia animation that I was looking for, but I can't seem to find it. Hello, click. And yes, here it is. Perfect. So this is a visualization kind of like what I wanted to make. Something like this. Just instead of focusing on the inner triangles, I want to focus on the outer triangles, because I think that's going to help with understanding a bit more. So this is somewhat like the visualization I want to make. Okay, let's go back to iterative function systems. This is the Sierpinski triangle, and here's the final result of the simulation. So I'll show the final image after this is all done, and show that it looks pretty much like the initial image that we had. So cool, we have that image done. Okay, so now here's the tricky part. Here's the thing that is kind of difficult to describe, and so I want you to let me know if this makes sense. So the next question is, what about a square? So when I learned about this for the first time, I began to wonder about other shapes. Could we create fractal squares, hexagons, circles? Such shapes seem like natural extensions to the triangular Hutchinson operator provided above. But there's a bit of a hitch. First, let's take 4 points, A, B, C, and D, this time located on the 4 vertices of a square like so. So again, the same image as we had before, A, B, C, and D. And in a similar fashion, we'll create 4 functions with Hutchinson of P is equal to, the union of these 4 functions here. We then create 4 initial points located at the edges of the square, halfway between the vertices, and allow these points to spawn 4 children each. If we then create 4 initial points located on the edges of the square, halfway between the vertices... Wait, what? Oh, I see what I'm doing. Halfway between... Yeah, okay, I see what I'm doing. So the idea is the following. We are going to do journal new page before. So this time we're going to have 4 points. I'm just going to draw it as this giant square in here. So we have point A, B, C, and D. So A, B, C, and D. And then we generate 4 children. These 4 children are going to be here, 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 and here. And if we do the same thing, that we did before, where we let these, some of them move halfway towards C, some of them move halfway towards A, some of them move halfway towards B, some of them move halfway towards D, instead of getting a fractal-like pattern like you did in the Sierpinski triangle, you actually will get a random distribution of points. Okay? And this is not what you'd expect, but you get a random distribution of points, right? So let's go here. It would seem that the final result is just a random distribution of points. So what happened to the self-similar structure we were getting before? Why isn't this more interesting? These are very good questions that I don't know the full answer to myself. If you have a satisfying answer, please reach out and let me know so I can update the text here. The best answer I have for now is that some Hutchinson operators are interesting and some are not. On the one hand, the square is a bit more interesting than it first appears. On the other hand, this square is a bit more interesting than it first appears, but I think this is easiest to understand when we use the Hutchinson operator in a slightly different way. So now we start talking about chaos games and attractors, right? So the idea here is that we have this triangle that we can generate by just iterating through all paths on our Hutchinson operator. If we do the same thing for a square, it doesn't work, right? So what I'm trying to do here is I'm trying to introduce the idea of an attractor, which is basically, without really... without talking about it too much, an attractor is essentially something that attracts points within a Hutchinson operator, right? So the Sierpinski triangle is the attractor of that set of Hutchinson operators. The idea is that all the points want to lie on that triangle, and once they're on that triangle, they don't escape. And the same is true for this two-dimensional box. If everything's on that box, it doesn't want to leave that box, so it's stuck on that box, but it's attracted to a 2D plane instead of a set of lines like it was in the triangle. So this is where I'm trying to go with that. Okay, so until now, we've been using the Hutchinson operator in a computationally costly way. Every iteration, we generate 3 or 4 new children, and they generate the same number of children, and so on. This scales exponentially and means that we'll quickly have millions of children to keep track of. A much more computationally feasible method to use the Hutchinson operator comes in the form of the chaos game. Here, instead of tracking down children of children, we track a single individual that chooses randomly between Hutchinson functions. For the Sierpinski triangle above, the code will look like this. So we have to add the code, but essentially, instead of following all the children, we just have one guy, and it just randomly selects function 1, function 2, or function 3, and by randomly selecting, it moves around and will recreate the Sierpinski triangle. After a few thousand iterations, it becomes possible to see the fractal again, and so we're going to add an animation of that. That said, there is something peculiar about the way the chaos game starts. Essentially, our lone child begins their journey at a random location. What if that location is off the triangle? Well, let's test that. If we start at a point at the center of the triangle, it will eventually find its way to the triangle itself. Let's see. Let me reread this. If we start the point at the center of the triangle, it'll eventually find its way onto the triangle, is what I should say. Onto. I think that's one word. And then all subsequent iterations will be on the fractal. Here I've plotted the steps where the wanderer is still wandering around looking for the correct shape. So basically what I want to show is all these points kind of moving towards the Sierpinski triangle. Okay, let me go ahead and catch up on chat, and then we'll keep moving from there. It's a box. I think I have an intuitive explanation for that. If you can prove the chaos game between 2 points is also uniform. Send me a message on Discord. I want to talk a bit more about that. Hi, back. Hey, Gibbous. I had cake to handle because of my sister's birthday. Oh, tell her happy birthday. I think infographics with some green checks and red crosses would go a long way at visualizing what's possible and what's not. Right. So we'll be doing that in a bit, but I'm interested to hear what you mean by that. Okay. Together with the text. Right. Well, we're adding those in just a bit. So happy birthday. We utilized modulo calculus with Gamozo to create a new computing architecture. Wait, what? Oh, I see. I missed your 2 other messages. Sorry. I finally cleaned up math. Cool. Gamozo is a Twitch streamer. Oh, cool. Sounds good. Nice. Gamozo Labs on GitHub chocolate milk project. You put it on Instagram? I don't know if I can go here. Can you look at images on Instagram? Oh, super cool, man. Huh. Nice. It's pretty cool, man. Instagram math. It's not my birthday today, but it's most of my family's birthday are clumped together in the same week, so it's all right. That's basically every Radix. I'm trying to remember what the problem was for why this was created. I know that it looks a lot like the... this looks like Fourier operator, right? But I'm trying to remember what math you were trying to solve that this was the solution. I'm trying to remember. I'm so sorry. Oh, you mapped every radix. Yeah, right. I understand now. Cool. Seriously, good job, man. I'm super stoked to see this. Good job. Okay. I'm going to keep going through this chapter where we're almost done, and then we can talk about what visualizations we need to make and how we're going to make those visualizations and stuff from there. Okay. Okay, so it would seem that the wanderer is attracted to the Sierpinski triangle with this set of functions. That is actually the case. The truth is that the word attractor is a very loaded term in the literature, but for the purposes of our discussion here, the attractor is any shape defined by the iteration through Hutchinson operator functions. So let's go back to the square. Before we saw a random distribution of points. Even with the chaos game, this will not change. However, we now know that the random distribution isn't truly random. Rather, it's an attractive plane where our lone wanderer can exist happily within. That is to say, if the two-dimensional square is itself the attractor for that Hutchinson operator. And if we start our journey person off on the square, they will eventually find themselves within it. Similar to the triangle before. The next obvious question is whether a square can create any more interesting fractally patterns, and the answer is yes, but only if we restrict the movement a bit. Which brings us to another topic entirely, restricted chaos games. Discussing chaos games in more detail is a chapter in its own right, so I'll forgo the discussion here. If you're interested, please let me know, and I will be more than willing to add the chapter in the future. So that's actually where I'm leaving it. Because, yes, we could do huge discussions on chaos games. There's so many things we can talk about with chaos games. But I think actually what I want to do is I do still want to move towards the fractal flame direction. So I think what I want to do is I want to start by talking about iterative function systems, mention the chaos game. Then the next chapter will be on restricted chaos games, and the chapter after that will be on fractal flames. That's kind of where I'm going with this fractal chapter. That's what I'm hoping for. The idea is that math can create a supercomputer waveguide. To get a slice of it takes multiplying by square root of pi log, whatever dimension or math operation you want a piece of. Yeah, man, so it's cool. I mean, it will probably be useful, right? I still need to kind of think about it a bit, you know? I need to think about where it's being used, you know? I mean, your idea is to optimize the computation on supercomputers, right? I'm sorry, I'm still trying to remember everything. I'm very rusty, you know? I'm sorry about that. For what you're doing, you're looking at a velocity distribution. Here? Hmm. Right. So you're looking at a velocity distribution. Velocity of what, though? I'm sorry I'm so bad at this. I really should know, but I've completely forgotten the discussions we've had before, and I'm so sorry about that. Let me get some water. Oh boy, I'm super hungry. Since I've come to the US, by the way, I think I'm going to put this on Twitter or something so people can see it. Just going to retweet it or something. Hey, Slater, how are you? Man, since I've come to the US, I've gained 30 pounds. For those of you in Europe, that's like 12 kilograms or something like that. I've just gotten really big, like not that big, but I'm not happy with that at all. So I've been slowly trying to restrict my diet, which means I'm, a bit hungrier than normal. So I'm a bit off than I used to be. But I don't know. Is it the American diet? No, it's my diet in particular. I just did a very bad job of keeping up with it. Jean-Louis Carol. Sorry, I totally mispronounced the second part. But thank you so much for following. Really appreciate it. Put sugar and carbs and everything. That is actually true. Like, you find sugar in the darndest of places. And I think that's true for everywhere. I don't think it's true specifically for the U.S. But I do know that there's sugar everywhere, and it's rough. So if you factor in Sierpinski as a log function of my formula, the baffles should show the distribution as an inverse square of pi, given the multiply by square root of log Sierpinski. Huh. I need to think about that a bit more. Okay, so let's talk about the visualizations we need. So first of all, what do you guys think? So should we... So here's the general flow for that chapter. Let's go journal, new page before. Here's the general flow for the chapter. We start by introducing Sierpinski triangle. So try that one again. One is Sierpinski. That's how you spell it. I promise. I'm like 90% sure. The second, we talk about square. So random distribution of points. Okay, so we talk about Sierpinski. And we say, okay, well, if we can create a triangle, the question is, what about a square? I guess we'll just draw a square here. So then we show that the square is actually random distribution, and we ask why. And so the answer to that is we talk about chaos games and show that if you're off of the attractor, your wandering point will be attracted to it. So this means that the answer to this is that the Hutchinson operator spans the attractor. So chaos and attractors. So that's the general flow for this. What do you guys think? Look at how much sugar there is in a coffee shop cup of coffee, except the I and N have malformed into an M. It's because I'm using a tablet. I mean, in real life, it'd be much worse. Okay. So yeah, if you guys have problems with this flow, let me know now, because this is the only stream I'm going to be talking about the flow of this chapter. I kind of like the flow a bit, so I'm happy enough with that. So now let's talk about the set of animations we need. I guess you could also talk about it on GitHub when it's eventually on GitHub. So the set of animations we need. Basically, we need to create the Hutchinson operator animation. So let's go ahead and look at that code, and let's talk about what we're going to do there. Because I've been talking, well, let's see, what time is it now? It's 8:30. I'm sorry, 6:30, my time. More than likely, I'm going to Let's see. More than likely, what I'm going to do is I'm going to stream. I'm going to stream for another 30 minutes or so. So I'm trying to figure out what we can fit in that 30 minutes time. So let's go ahead and get the animations that we have up and running. I'm kind of de-rusting myself a bit. So let's just see where we go from here. So let's go ahead and Control C here and quit here. Right, quit here. I'm going to go ahead and commit the changes that we just made. So -m. Small modifications. We'll say text editing here. Yeah, I'm gonna commit this. I'm gonna push that up. Git push origin IFS, just so it's up. And see what we can do. Oh no! Oh no, I didn't. Oh gosh. Oh no. Welcome to the merge conflict land. Wait, what? Git push origin IFS. Failed to push some refs to... Is this gonna work now? I'm confused. What happened? Oh, it's because I rebased. Okay. But now I'm terrified that I accidentally am deleting something. So let's do GitHub and make sure that I'm not... Oh gosh, I was really worried there for a second. The threat of merge conflicts is not something that I take lightly. Algorithm archive. Let me... Actually, I want to go to Laos algorithm archive because that's where I put this. Okay. And we're going to go to IFS here. Right. And let's see, what's the last commit? The last commit was fixing IFS typos. Let's see what I have here, just to make sure I'm not doing something. With great double dash force comes great double dash responsibilities. Yeah, git log. Right, so this should be last. So git push origin IFS force. I really like that quote, actually, recursive chat. That's pretty good. 30 minutes speedrun coding, easy every time. So for one dot, are you looking at the inverse square as a modulo per vertex? I don't know what you're talking about here now. I'm sorry, I'm lost again. So we're gonna CD into projects, simuleos, and we're gonna CD into fractal here, and let's do the same thing over here. CD projects. Okay. CD projects, simuleos, fractal. I should be able to run the last G++. Nope, that's still the old one. Okay, so what am I computing here? There should be ls*.cpp, and we're gonna. I'm so sorry. I misspelled Sierpinski every time, and now it's just like a meme. I can't I can't spell it right. No matter how many times I try to spell it right, I get it wrong every time. So just, I'm sorry. I'm sorry for just. I'm sorry. I'm gonna fix all the Sierpinski names in just a second. Okay, so that's gonna be Sierpinski.cpp, and let's just run that. And while that's running, let's fix all of these guys, so they're actually the right name. Y. Okay. Vi. Let's go ahead and move. Git move. Sierpinski. .cpp into Sierpinski.cpp. And now we're going to go here, and let's just run /Sierpinski. Okay. That did something. I'm actually not sure what it did, because I don't remember the last visualization I was showing. So let's go ahead and fix this in here. Sierpinski.cpp. And let's just look for Sierpin. Change that to an I. Next. Change that to an I. Next. Change that to an I. Next. Okay, so that one's actually spelled correctly. Let me catch up on chat. Given two positive numbers, wait. I'm fine with whatever. I can read code, but your high-level math and physics is not yet within my reach. Fair enough. I don't know much about pad. It's okay. I should probably... That's a question of where we should attack the algorithm, where the algorithm archive should be. There's some things that just require a bit more math than other things, and unfortunately, when Some things can just be better expressed in math, you know? Like, that's just how it is. If you show the math, it becomes easier, in my opinion. But the problem is I am selling intuition, right? So the math has to be coupled with visualizations that adequately describe that. Given two positive numbers, a and n, a modulo n is the remainder of the Euclidean division a by n. Yes, that is correct. I mean, you want the difference or the tangent of such. Right, that was my question. I don't know, what am I trying to get? What does the tangent show me? Quick question. The Sierpinski triangle can be generalized into 3D. The Menger sponge is like a 3D version of the square that you mentioned doesn't work. However, you can take a 2D face set and get a version of the square. Does that mean the IFS needs to be a fifth function? Needs a fifth function for the middle to be generalized? Right. So just for the record, oh, I might even have it up. No, I don't. Iterated function systems. That's a very good question. This usually comes in the mind. So here's a Menger sponge, for example. But I'm looking for chaos game instead. Sierpinski chaos. Oh, yep, I'm looking for chaos game. So if you, here it is, the Menger sponge. So it's also called the Sierpinski carpet. So if you set the jumps instead of being to half the distance between A, B, C, and D, and instead make it 2/3 the distance between A, B, C, and D, you can then create what is essentially the Menger sponge. So it's not that you need a fifth function as much as it is you need to modify the 4 functions you have in order to create this. By the way, IOFU, thank you so much for following. I'm sorry I missed that a few minutes ago. So that would be my answer there. And again, this is part of the restricted chaos games, which I don't know if that's necessarily what we want to do. So the tangent will show you the geometric distribution, just like you would, say, a triangle or sine wave. Right, okay. I think I'm kind of getting, understanding you. Metastatic, that's super cool. Yeah, it is super cool. There's a lot of super cool things about this that I really like. The way I see it is, this is my question. Should we go into the restricted chaos game here? I think the answer is no, because there's so much depth we can go into here. I don't see any reason to force this into a shallow discussion on just iterated function systems. I feel like this should be part of a greater discussion, which would be chaos games themselves, and in particular, again, restricted chaos games, because there's so many cool things you can do with them. And again, this goes into the fractal flame method, which we did a while ago. I think even here we can show you some fractal flames that we generated. Brain quit. lsstar.png, and I think I can just open it up. Mirage banner.png. Oh, right. So here's some fractal flames that we generated. Here's like a heart that we generated, and these are again via iterated function systems and chaos games. It's just that it's done in a way to make it like super visually appealing and stuff like that. So you do blending and all this other stuff. Now. Foldster, who may still be in chat, has a significant number of these that look fantastic. And so there's a lot of stuff that we can do here. Oh, there's the tree. Man, I've been trying to put videos out for iterated function systems for a long time. I just haven't gotten there yet. So we're getting there now. I promise we're finally getting there now, and I'm happy that we're finally getting there. Okay, so let me see what visualization actually came out here. I'm pretty sure, CVP. Right, so let's go ahead and run this one. So I'm gonna run the last G++, and, ooh, hello. Because I changed Sierpinski to Sierpinski with a I. So let's change that really quick. I've got some crazy stuff. Yeah, you've got some amazing stuff is what you have. Okay, now we're gonna run Sierpinski. And what we should see here is just a basic Sierpinski triangle. That's what we should see. And then we need to start talking about the hard stuff. The stuff that scares me every single time I start going back. Like, for the past 2 months, I've been terrified of writing this code. Because, first of all, it's not essential, so I don't have to do it. But it's just, I'm terrified of it. I'm absolutely terrified of it. I can link my Fractal Flames folder in chat. Yeah, please do. I think it's really cool. This basic math that I would find for your question. Yeah, I just don't understand how this is related is the problem. I'm sorry about that. Yeah, I just don't know how this is related is the problem. Right. So, okay. if looking at one vertex. Um, again, I'm not sure how this is related. I'm sorry. I'm not smart enough to figure this out. So let's go back here. We should have the visualization up. Oh no, it's not done yet. Oh, but I will take a look at these while we're waiting for the visualization to finish. Let's go here, take a look at there. And let's see what we got. 40 animations. Whoa. I didn't even know. I vaguely remember this. And so you're doing a projection, I assume, from 4D to 3D via, what, stereographic or something? Nice. Nice. These are so cool. One day. When I grow up, I want to be like Folster. That's what I want to be like. Man, these are so cool. Just taking the first two coordinates. Right. Oh, you're just taking the first two Wait, what do you mean you're just taking the first two coordinates? So you have a 4D system and you have to multiply it by some three-dimensional matrix. Harry building these? Oh yeah, I'm sure he has a thing. Gen 3. I'm gonna look at your Gen 3. Gen 2 was my favorite generation of Pokemon, but you know. How are you building these? Let's see. Also, why are they all .gifs? Are they... Oh no, only some of them are .gifs. Right, a lot of them are PNGs. Let me grab some water. Ooh. Man, these are so cool. Yeah, they're cool. Gen 2 is definitely the best gen. Gen 1 and 2 were supposed to be one... Wait. Gen 2 is definitely the best gen. Gen 1 and 2 were supposed to be one, but cartridge limitations. Honestly, Gen 2 folder is better. We'll go back to Gen 2 then. What do we have here? Ah, man. These ball ones are super cool. Man. You're making me want to get back into fractals, man. Specifically fractal flames. As far as Pokemon is concerned, yeah, Gen 2 was my favorite gen. My favorite Pokemon is in Gen 2. And also I just like the fact that you could go back to Gen 1. It was just a good game, you know? I argue it was probably the best bang for your buck of any Pokemon game that you got. Admittedly, I also liked Colosseum. It was one of my favorite Pokemon games as well. But I just like the idea of purifying Pokemon. That was good. Let's see. I did some to-dos in my script I was coding. You know, some days are like that. Some days you just have a bunch of to-dos and you just get through them. And those are the best. Those are great days, in my opinion. It's the days when you have a list of things to do, but you can't get through them for some reason or another that suck. You know? Like, man. Okay, I'm going to stop looking at these. I think our Sierpinski triangle animation is done. I'm just going to show it on screen for a bit. So let's go ahead and run MPV. If I run the last MPV... No, that's not the right one at all. In fact, I hope my face is still moving. Yeah, okay, I'm still fine. Okay, so what we're going to do is, let's see, let's go ahead and do MPV, temp, video, MP4, loop, 0, and there should be a simple Sierpinski triangle animation. And that is all it is. Nice. Okay. Unfortunately, there might be a bit of backtracking for the rest of today's episode, describing what we're going to do tomorrow and stuff like that, because 20 minutes left isn't enough for me to actually get much done, but I can describe what the problem is. To be honest, I was super salty when Crystal came out, and they just gave you Suicune, though. Took me so long to hunt down that in Gold and Silver. Man, I understand that. I understand that a lot. Man, I miss just being able to play like Pokemon and stuff like that, and just enjoying my time playing the game, you know? Like, nowadays, every time I play a video game, I just get guilty. Like, I feel like I should be doing something else, you know? I don't know. I feel like maybe a lot of people here can relate to that. Funky Monkey, hey, how are you? Okay, so here's our Sierpinski triangle animation. Let's talk about the elephant in the room, and that is the Hutchinson operator traversal. I want to go somewhere with my life, but I don't know where that is. Ah, it's here. I know exactly where I want to go. I'm going to close this animation. It actually does use, apparently, a significant amount of processing power. Okay, so let's do this animation. Journal, new page before. If you guys were here about a month ago, you knew that I was very into trits, which are bits, but in like a trinary system instead of a binary system. So here's the animation I want to make, right? I'm going to have point A, point B, and point C, right? A, B, and C. That's supposed to be a B, not a 3. And the idea is that all of A's children are going to move around. So one's going to go halfway between B and C, the other's going to go halfway between A and C, and the other's going to stick on A, right? And B's going to have 3 children as well. You know, one's going to go here, one's going to go here, and the other's going to go here, right on top of B. And then C's going to have 3 children. One's going to go here, one's going to go here, and the other's going to be right over here, right? Ternary should have been the one true light. Binary was a mistake. Right. So now the issue is, what we have is 3 initial points. So we have one starting at A. We'll change color here. We have one starting at A, one starting at B, and one starting at C, right? And then all 3 of these spawn 3 children. One goes, each one go according to one function, right? So we have one going through function 1, 2, and 3. 1, 2, and 3. 1, 2, and 3, right? Okay, so now we do the next generation, right? So then we have all of these points here. So all of A's children are now generating new children. So we have one that goes here, one that goes here, and one that goes here. You know, all of B's children then generate new children. So you have one here, one here, and one here. And then all of C's children do the same thing. So you have one, I think I put that in the wrong spot. I think B is supposed to go here. Yes. And then C's children goes here. And I think the other 2 spots are already taken. Halfway between A. Yeah, so the other 2 spots are here and here. Okay, so this means that, you know, all 3 of these kids then generate a new generation of kids. So they go 1, 2, 3, 1, 2, 3, 1, 2, 3. Right. I hope this is making sense. So the idea here is that what we need is we need to span all possible movements across this tree, right? And that's the issue, right? Because essentially what we're doing to create this animation is a breadth-first search through all layers of said tree. That's what we're doing. And so the question is, how do we do a breadth-first search of a tree that could have n generations, right? So here's generation 1, here's generation 2, but it could be 3 ... n. We could have a huge number of generations, right? So the question is, how do we do a breadth-first search in such a way that is computationally feasible, yada, yada, right? Betty Han, thank you so much for following. Really appreciate it. Ternary should have been the one true light. Yeah, I figured out why square is uniform. Cool. Please send me a message on Discord. I'm willing to. I would like to hear more about what you think about that. Because my vague understanding is just, you know, the Hutchinson operator spans, you know, some sort of attractor, and that attractor in this case happens to be a plane. And to me that makes sense. But I know it doesn't make sense to a lot of people, right? So I need to kind of find a way to make this make more sense, you know? Okay, so what are we going to do? Well, okay, let's say we're trying to get to this child down here. Well, this is just using function 1 and then function 1 again, right? And let's say we're trying to get to this child down here. Well, that's function 1, function 2. And if we want to get at this child, it's function 1, function 3. So in order to get to any of these children in here, all we need to do is go through function 1, right? And then function either 1, 2, or 3, right? So to go through these guys in a breadth-first fashion, all we're doing is counting trits. We have 0, we have 1, and then we have 1, 1, 1, 2, and 1, 3, right? So what we can do here is we can create a numerical system that allows for us to traverse through the tree simply by counting upwards. That way we don't have to hold a huge amount of data, a potentially huge amount of data on our system, right? So the question is, how do we do this counting appropriately so that we can keep track of where we are on this tree, right? Because in the end, what I'm going to do is I'm just going to create a giant trit string, you know, whatever this trit string is, 1, 1, 1, 1, 1, 1, 2, 1, 3, or something like this. And this will indicate, you know, you have A, right, as your initial point, and you're going to be using function 1, function 1, function 1. Just going to delete some of these ones. Function 2, function 1, function 3. Uh, oh boy. On A. And that's how you get to that point. So that's kind of what I'm trying to do here. So if you have some sort of trit string, you can then iterate through. And so the reason I really want to do this, I know we could do it the dumb way. We don't need to do it this way. But the reason I want to do it this way is because I want to make 2 videos out of this. One, I want to make the iterative function system video. But the other one, I actually just want to talk about this as a computational curiosity of mine. Just something kind of interesting that came about during stream based on discussions, and I think it's pretty cool. Lucky Boy, thank you so much for following. Also, AI Swigart, thank you so much for the raid. I really appreciate it. By the way, I have not seen your stream before, but or maybe I have and I've just forgotten. I hope you guys are all having a wonderful, wonderful time. And also, how was your stream? I hope it went pretty well. For those of you coming in, hi. I hope you guys are all having a wonderful day. I work on a project known as the Arcane Algorithm Archive. It's over here. It's essentially a way for us to teach algorithms. It's a book in a way, right? So the idea is, like if you go to, I don't know, Bubble Sort or something like that, let's do Gaussian elimination. We give you a description of Gaussian elimination in a way that you would get from maybe numerical recipes or something like that. We truly try to describe it so that people can implement it themselves. And then we provide implementations in a large number of languages, all provided by the community, right? And so the idea is that we're writing a book and also creating YouTube videos for said book. Again, the YouTube channel is going to be LeosOS, so youtube.com/LeosOS. So here's that as well. So here's that, and here's the algorithmarchive.org. There you go. So those are links to what I do. What do you do? Al Swigert, how are you? Great, we just work on random small Python games. I added a quick description to the Algorithm Archive channel. Oh, cool, thanks. I'll take a look at that after stream. I don't want to look at it right now. Messerious Physics, thank you so much for following. Really appreciate it. So right now we're working on a particular problem or a particular algorithm known as the iterated function system. And this allows for people to generate like images such as those here, like just random fractal patterns and stuff like that. The most famous iterated function system is probably that of the Sierpinski triangle, which is here. It's just a triangle of triangles. And right now we're doing what we can to make this intuitive for people to understand, right? So what I'm working on now is a visualization, not of just this, which it's kind of hard to see what's happening here because you have 3 points and then you have points that are just randomly generated and the picture all comes at once, right? So instead what I want to do is I want to soup up another animation that is on Wikipedia to make it even more visually understandable, right? So I'm going to try to create this image right here. So let's go ahead and start. Let's talk about this visualization and where we're going with this visualization and what I want to do with it. So I'm just going to redo this description that I just had over here on my little chat here. It'll take like a minute or two. So sorry for those who were already in stream and they saw it before. Hopefully you don't mind me going over it again because it is kind of complicated and difficult to describe. Now, unfortunately for the new raiders, I will only be streaming for another 15 to 20 minutes. This is in part because I'm super hungry right now, and in part because my stream time is usually from 6 to 8 p.m. Eastern time. So I just got, I was just about to recommend that same Wikipedia animation. Right, I think it is intuitive, but I think it could be more intuitive, and that's kind of where I'm at right now. So what kind of games do you make, man? What did I just do? Okay. I'm up here. Okay, so what I'm going to do, so for this animation, we're going to have 3 initial points, A, B, and C. Okay, and we're going to have 3 functions, function 1, function 2, and function 3. Now, all 3 of these functions together form an operator known as the Hutchinson operator. Function 1 will take whatever point you have, add A to it, and divide by 2. Function 2 will take whatever point you have, add B to it, and divide by 2. And function 3, it's supposed to be a 3, let's turn that into a 3. There we go. We'll take whatever point you have, add C to it, and divide by 2. So if you take A, and you iterate, and you let A generate 3 children, you'll have 1 child that goes through function 1 and stays put because it's, the point, which is point A plus A divided by 2, it's going to be A. You have another point that's P plus B over 2, so it's going to move halfway towards B, and another point's going to move halfway towards C. If you do the same for the other children, you're going to have 1 here, here, and here, and 1 here, here, and here. So here's the issue, right? Here's what we're talking about. So we're going to have point A, point B, and point C as the initial points for all the children, right? Then all 3 of these guys are going to generate 3 kids. 1, 2, 3, 1, 2, 3, 1, 2, 3. And all three of those guys will generate 3 kids, right? And they'll also move, you know? And if you know anything about algorithms or we'll say tree traversal or anything like that, we're essentially creating a large tree that we have to traverse through breadth first. Which basically means we have to go through each level like this. We're going to have to go, let's change this to blue. We're going to have to go 1, 2, 3, and then we'll go 1, 2, 3, 1, 2, 3, 1, 2, 3. So we have to find a way to go through our tree in that fashion. And this, of course, is called breadth first, because we're going through the breadth of the tree first. Okay? BFS, also called the breadth first search. Elsewhere, I was just about to recommend that same animation. I've been working on a huge collection of simple text-based games for beginner programmers to read as examples of complete programs. So more than just code snippets, but not the source code for full-blown professional open source projects. Actually, look, if you've been making text games, I'm a big fan of terminal games. Like, I've been wanting to make terminal games for a long time. Let's see. I mean, we did some animations in the terminal. I've actually been recently really into Sixel, which is where you can do like real animations in the terminal and stuff like that. Lots of really cool stuff to do. I'm a big fan. Let's see, try to keep them under arbitrary limit of 256. Under 256 lines, that's actually rather impressive. 1 second. Let me just... But yeah, it sounds like you're super cool. I'm going to give you a follow really quick. Let's see, what do we have here? Because I'm interested in seeing your stream later. Oh. Cool. Okay. Right. And right, thank you so much for following. Really appreciate it. Elsewhere. Okay. And also Relax F, thanks for following as well. Okay. Right. So again, guys, I do apologize that you kind of came to the end of stream. I'm basically talking about what I'll be doing next. But, you know, if you have somebody that you want to raid at the end of stream, please feel free to let me know. I've got a list of people who I would normally raid. So, like, some artists, but also Seam Griffing, Dowright, Kello Creation, I think, as well. So if there's somebody in particular that you want to raid, let me know, and I'll raid that person at the end of stream. Okay. So, how are we going to do this animation? What I want to do is I want to create a trit string of operations that we want to iterate through. So by this I mean if we have a string that is 1, 2, 1, 1, 2, 1, what this means is we're going to be going through function 1, function 2, function 1, function 1, function 2, function 1, right? So the idea is we're going through the tree in this fashion. So what we're going to do is we're going to continually recompute the point's location at every step, right? So in this way we can do a breadth first search simply by updating this value, by counting up in this trit string. We can then iterate through in a breadth first fashion. I think this is somewhat common. I think people know about this, but I kind of didn't a while ago, so I learned about it on the fly. And again, I do want to make a YouTube video about first iterated function systems, and then also this particular trick that we're using to go through a tree in a breadth first fashion, because I think it's kind of cool. And we already have a video about tree traversals, so I don't know. I think it's nice. I think it's a cool thing to do. Okay, so what I'm going to do right now is I'm going to look at the code that we have, and I'm going to see what actually needs to happen, because quite frankly, I don't know. So Cropeb, a while ago, I believe, was the one that wrote this implementation that we have right now, where we have an increment and a print for what he called trites, which are essentially trits, like that trit string that I showed before. When point A's child meets the halfway point between A and C, does it occupy the same position as the opposing C's child? In this... yes, in this visualization, yes. I'm not gonna make this more complicated than it needs to be. Sorry. What I'm probably gonna do is I'm probably gonna give all the children an alpha value, so that if two children are on top of each other, their values add together a bit. And I think that might be a good way to do that representation. But we'll see how it goes when we actually do the animation. So. Right. So that it just depends on what we do there. Gratsugo, thank you so much for following. Really appreciate it. Okay. So, this is a bit of hard code to understand. So what I'm going to do is I'm going to describe what this code currently does and how we need to modify it, and then we'll do the modifications on tomorrow's stream. I realize it's a bit of a weird way to work with it, but the truth is I need to just take a second to theoretically understand what I need to do. And then after I get that understanding, we can then do it on the next stream. But the thing is, I need to get to that point where I can start asking myself what we need to do. And I'm not there yet. So yeah, we need to go from there. Okay, so we've tried increment. What is this doing? So we have an LL, and an LL is a long. So what this should be is it should be a pair of bits. So it should be 0, 0, 0, 1, 1, 0, or 1, 1. It's just a pair of bits. And what we say is while increment. So while we're incrementing this guy, we're going to say LL, which is another long, and it's going to be 4, 2 is equal to number.first, and increment. Okay, so we're using bitwise operation. So we're using the bitwise AND operation here. What we're doing is we are outputting the bitwise AND of increment, which is just 1, right? So that means so here's what we're doing. We're going to have a 0, 0. And this 2-bit operation is going to represent our trit system. Ideally we could just use trits, but we don't have trits. So what we're doing to increment this is we're going to add a 0, 1 to this system, right? And then overflow it if necessary, right? So, it's going to go 0, 0, 0, 1, 1, 0, 1, 1. And what we need to do is we need to find a way to identify these guys in our trit alphabet, or our trit, alphabet's one way to put it, but in our trit system, our trit number system, right? So we have LL42 is equal to number.first and increment, and then we have overflow is number.second and increment, so we're going to add 1. I guess it's add 1 to both of them? Yeah, I'm going to have to look at this code a bit more. I'm actually at a step where I don't know actually how to read that. So we had number.first. I don't even know what this operator is, honestly. Let me look up bitwise operators and see. See, I should have... Yeah, okay, bitwise. I don't think I put the caret operator in my bit operations chapter. XOR. Okay. So we have XOR equals. Oh boy, this is not straightforward at all. Okay. And then afterwards we bit shift the overflow. Oh boy. Ugh. Okay. And let me see. So I think this just increments. And then this guy down here prints the trit. So what are we saying here? So if number.first and I. So for int I equals 1, I bit shift trits minus 1. So I think we're just going through each element there. We say if number.first and I, we're going to output 1. If number.second and I, we're going to output 2. Else we output 0. Okay, so I think actually what we need to do here is we don't need to change the incrementing here. I think what we need to do is we need to change how we're interpreting that incrementing. And I think that's what we need to do. So I'm going to go over here, G, and I'm going to output 2 things. So I'm going to output, you're going to have to while loop it. I don't think so, but we'll see. So here we're incrementing. Let's see, what do we have here? So for the Hutchinson operator, right now I just have print trit, and then we have this. So we should have the trit, and what we're going to do, so the value is going to be 4, and we're incrementing the value afterwards. So I also want to do std cout, and what I'm going to do is I'm going to output value dot first and new tab, and then the value dot second. I think that's what I need. And then let's go ahead and new line there. Okay, let me make sure that's what I'm looking for. Number.first, number.second. I think that's fine. Okay, so let's see what I'm getting here. So we're going to do G++, and it's giving me an error. It's giving me an error because I put the semicolon in the wrong spot. Okay, so let's go ahead and run /Sierpinski, and let's see what this has. Okay, that's clearly different than what I was expecting. So 0, 0, 0, 0, and our value dot 1, our first value is 1, our second value is 0. Okay. Right. This is dramatically different than what I was anticipating. Okay. Well, this is good. So we know what we need to do, and we will come back tomorrow and we'll get that done. Right. I do apologize for the streamers who came, or for the. It is iterating, right? But it's not. Yeah, it's iterating, but it's not a while loop. It's a for loop. Okay, I think this is actually where I'm going to leave it today. So we know what we need to do. We know what the visualizations are that we need to have. We know what we need to do with the algorithm archive. Basically, today's stream was figuring out what we need to do, setting up a kind of schedule for when it needs to be out. And right, I think I'm happy enough with this right now. So I need to take some time to figure out this trit code, and then we'll work on that again tomorrow. There's just not enough time for me to really hop into it now. Okay. So let's see, who do we want to raid at the end of stream? We could do Go Pirate Software. They're playing World of Warcraft. CM Griffin, what's he doing? I think he's doing hacking stuff again. Talkative Tuesday. Okay, Dowright is doing Prevent Digital Pandemic, Python Deep Packet Inspection. Keller Creation. How about we do Dowright today? I think we'll do Dowright. So let's go ahead and do that. Or we could do, what's Callow Creation doing? Naivebot, SFX, GFX. Frick Chemist is live. Hunting buggers under the microscope. What do you guys want? Do you guys want chemistry, art, or computer science? I imagine you guys want to do more computer science. So let's do CM Griffin. Or Dowright. I feel like I did CM Griffin before. So let's do Dowright. So let's go ahead and raid that. So let's do raid Dowright. Okay. So that's it for the day, guys. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos, when we implement the trit solution, get some really cool visualizations out, and hopefully get this chapter mostly underway. We'll see how, it's going to take longer than one stream, but we'll see where we go. Thanks, guys, so much for coming in. I'll see you next time. Bye, guys.